Actually, if you look back in the parts we've covered, if you go back to part 3, this is analogous to part 3 except for weak bases. So part 3, we talked about weak acids and we did an ice table. Same thing here, about weak bases. And I kind of let you guys in. It's not a secret or anything. I told you that I relate more to acids, more easily to a proton donor than a proton acceptor, but it's definitely a player. So you might see, if you see CH3COO -1, hopefully you're like, that is just itching to accept a proton. Okay, a whole negative gives it away. And actually, CH3COOH is acetic acid. And actually, the next part's going to talk about kind of these what we call a pair of species that differ by a proton. So this is going to be actually a base sort of deal. So we're going to put this in water. And here in a minute, you're going to see it abscond, take a proton away from a water molecule and leave the OH minus on the product side. Okay. So anyway, I don't know. Maybe I'll go ahead and kind of draw what I did before.
So I had a question. I was trying to think what it was. With that, the online homework, so we have just a trial for 14 days. Is that what that is?
No, if you use the code, you've got it.
For the rest of the semester?
Yeah.
Okay.
$40 value.
Sweet.
Right. So anyway, I just think it's kind of fun. Yeah, and you saw, when I tried to click on it, I had problems it opening the one I wanted. Like, it opened like 3 down, and I don't know, so hopefully you're getting to it.
Yeah, that works fine.
Okay. Yeah, they're excited I'm trying it. And then I just have to convince Carl, Dr. Snipes, that he needs to use it too. So remember how this works is you got to think about chemistry. What that thing is going to do in the molar amount is 0.10. What it's going to do is, if we have water in here, it's dissolved in, to a certain extent, it is going to take a proton from a water molecule. And then if you picture that in mind, you're like, oh, well, what does it look on the product side of the equilibrium? Well, it looks like the protonated form of this, CH3COOH, okay? And then this one without a proton. So that's what's going on there. Okay, so that is the chemistry. The KB is given, and you know we can write any equilibrium constant expression. And it looks like this. So CH3COO. That is acetic acid times hydroxide ion divided by this guy. Okay, and the KB is given 5.6 times 10 to the negative 10. All right, cool. So yeah, that equilibrium is this equilibrium. Oh, I was missing a C. Oh, I thought that didn't look right. Sorry, guys. My bad. Sorry, guys. Yeah, that makes me oh yeah, there we go. Okay, and then the equilibrium constant expression. So these KB, the Ka is called the ionization constant. And I just call the KB is it also an ionization constant? Okay.
I don't know.
I think it might be something else. Yeah, I think it's called I think it has a different name to it. All right. So you should start there. Here's our ice table. And you're like, well, how do things fit in? Well, you figure, remember we have this 0.10 moles per liter. We're going to actually say that is our initial, this guy, and we don't have anything else of the other two, kind of like we did with our weak acid. Okay, so this is a weak base, and we made it 0.1 molar, and then we put in our x's. Okay, so the CH3COO -1 is going to decrease, so it'll be minus x, and the other two are going to increase. And we take the initial and apply the change, and there are equilibrium concentrations. This should feel kind of vaguely familiar. And we take those equilibrium concentrations and plug them back into our KB expression, and it looks like this. And kind of deja vu back to last unit of material, we said that you can actually now come up with use the quadratic equation to solve for x. But what we've been doing for this unit of material is introducing a simplifying assumption. And don't forget to write your simplifying assumption. So what is our simplifying assumption? Is that x is significantly small relative to 0.10 molar. 0.10 molar is the concentration of our weak acid. Sorry, weak base. I'm sorry about that. Concentration of our weak base. So what we're saying is that at equilibrium, you're basically still going to have 0.10 molar CH3COO -1. By the way, let me go ahead and give a name to that. I've been calling this acetic acid, and it is. That's this guy. This guy is the acetate ion. This guy right here.
And it's a base.
What's that?
It's a base.
Acetate, yeah, it's a base, acetate. And the reason it's a base, it's a proton acceptor. Yep. And then here, in the next part, we're going to actually call these guys a pair, conjugate acid-base pair. So. All right, so things start to fall into place. If x is really small compared to 0.10, then that term in the denominator becomes 0.10. So now we're going to see it here in a minute. It'll be x squared in the numerator divided by 0.10 is equal to 5.6 times 10 minus 5. Again, this is kind of a deja vu from 2 parts ago. We said that the simplifying assumption works pretty well as long as you have this relationship between the molar concentration, in this case of your weak base, and your Kb value. So if we take Kb, which is 5.6 times 10 to the minus 10th, and we take times 100, so you're looking at 5.6 times 10 to the negative 8. Okay, so our 0.10 is greater than 5.6 times 10 to the negative 8. So you would think that you're going to be in good shape going this kind of easier route. So our Kb expression, that's what I call it, becomes x squared over 0.10 is equal to 5.6 times 10 to the negative 10th. Now it's very common to make a mistake at this point. You don't want to make a mistake, so I kind of think of it as kind of cross multiplying, flattening it out. So I'm going to take my 5.6 times 10 to the negative 10th times 0.1, so that'll make it times 10 to the negative 11th, right? And I'm going to have to take the square root of that. So x will be equal to 5.6 times 10 to the negative 11th, the square root of that quantity. 2 sig figs, and you get a value for x of 7.5 times 10 to the negative 6th. And here's where, like, I'm a firm believer in an ice table, because now I can say, well, what was x? Oh yeah, x was the important thing that we're going to focus on here to finish up the problem. X is the equilibrium concentration of the hydroxide ion. So working problems with weak acids and weak bases and all that, buffered solutions, we're going to be talking about those next week. You have to kind of identify what's going on to make it not neutral, or will it be neutral? And this is it. So we go ahead, and I think we're supposed to knock out some quantities related to the hydroxide ion concentration. Oh, by the way, there in green it says that if you were to not apply the simplifying assumption, you get the same value for x. So that's kind of nice. P.S. So let's knock out the other kind of 4 quantities now that we have the molar concentration of the hydroxide ion. We could go for the hydrogen ion concentration this way, recognizing that in a dilute aqueous solution, relatively dilute weak base like this, if we multiply the hydroxide times the hydrogen ion, it's got to be Kw. Kw is 1.008 times 10 to the minus 14th. We rearrange that, solving for the hydrogen ion. Hydrogen ion is equal to 1.0 times 10 to the negative 14th divided by the hydroxide ion, which we just got. So hydrogen ion is equal to 1.0 times 10 to the negative 14th divided by 7.5 times 10 to the negative 6th. And you're looking at a hydrogen ion concentration of 1.3 times 10 to the negative 9th moles per liter. Again, this is consistent with all what we've talked about basic and acidic solutions. We figured that tipping point at 25 degrees Celsius is 1 times 10 to the negative 7. Okay, so yeah, we've got less hydrogen ion than we do hydroxide ion. So we need to knock out the pH and the POH. We can do that. The pH will be equal to negative log of the hydrogen ion concentration, which in this case, pH is equal to negative log of 1.3 times 10 to the negative 9. Rounding it to 2 sig figs, and those sig figs are shown after the decimal place. You're looking at 8.87 is the pH. One of the things that a little bit of playing I've done with Alta, the online homework, is it does everything an instructor might want it to do with regard to keeping us on track with regard to rounding and everything. One of the things with Alta homework that I don't know why it's just having brain dead or whatever, but if you have to in Alta, if you have to put in this number in Alta, okay, you'll play around with it, but there will be a box for you to that has like 1, 2, 3, like to click on, and here's your entry box. So enter here. And here are the things, the little boxes you can click on related to your entry screen. So what you have to do is put in the coefficient. So I put in 5.6, and then one of the boxes right here is an X. Okay, and that means times. There's another box, and I don't know if maybe it's over here, that kind of has a cursive X, and that's the variable X. So you do this, X, and then over here, there's a box that has like, for superscripts, it'll go 10, it'll go, I think it goes box with a superscript box, like that one. So then after I do my multiply sign, I click on this, and it will automatically come up, and it's looking for, in that box, I would put 10, in that box, I would put negative 10. So I don't know if that helps, but that's kind of the, but it took me a while. I'm like, it won't take my answers. I know that's the right answer. So let me know if you're running into any snags. I think we're supposed to finish this out. Do we need to? Oh, I guess not. We could come up with a POH too, but that wasn't what they asked for. Okay. All right. Last part today. Gonna be a short one, people. It's funny, my classes aren't equal, so like my intro to Gen Chem, I'm farther behind, so they had to stay a little bit longer, but my physical science, I'm ahead. So I don't know. So I've been kind of talking about these. Actually, Dr. Snipes or my husband or Carl or whatever, he actually covered this unit or this part earlier. So, but I've been kind of alluding to it. So on either side of the equilibrium arrow, or for dealing with acids and bases, you should be able to identify actually 2 pairs of species that differ by a proton, and you have found a conjugate acid-base pair. Okay, so for instance, just kind of showing you, the HB stands for some sort of weak acid, and B minus stands for the weak acid that has lost a proton. You see the proton coming and going on either side of the equilibrium arrow, quite clever. Okay, so that is your conjugate acid-base pair. I know here it says this is the acid and the conjugate base over there, and this is the base, and then the conjugate acid over there. You see, with semantics, I just go conjugate acid-base pair. So I don't care which direction it's going. Okay? But I guess technically, if you're going from left to right, this would be the acid and its conjugate base. If you're going from right back to left again, this would be the base and its conjugate acid. So I've got some examples here. I can't remember. Do you guys already have all these? Yeah. Okay, cool. So water and the hydroxide ion, conjugate acid-base pair. So which is the acid and which is the base? Well, we look for the one donating the proton, the acid, the one accepting the proton, the one that has lost a proton is its conjugate base. Hydronium cation, acid in its conjugate base, water. We talked about how that sulfuric acid is a polyprotic acid. Of course, the first ionization gives you basically all the hydrogen you're going to get, a little bit from the second deprotonization. Anyway, so we call the donor over here, H2SO4, the acid. This is the bisulfate cation, and it's actually the conjugate base of H2SO4. Differ by proton. HNO3, this is kind of a weird one to be showing because actually the other one's kind of a weird one too. It's a strong acid, so I don't know where we have equilibrium arrow there. I'm just going to go with it. But this would be the acid on the left and its conjugate base on the right. Ammonium NH4 plus is actually weak acid, and its conjugate base would be ammonia. One of my least favorite things in chemistry, ammonium. Okay. Again, this is weird to see a two-way arrow, but I guess we'll go with it. We have the acid donated proton on the left, and then on the right we see the species without a proton.
We just call ammonia storage organic.
What's that?
We just call ammonia storage organic.
Ammonia storage organic.
The model that you had with the or no, that was vinegar, wasn't it? I keep getting confused. It had like storage organic written on it, and I didn't like see the label on it. What's storage organic?
Oh, yeah. Yeah, vinegar is acetic acid, so.
So isn't it true that the acid always turns into the base on the other side, and vice versa? The base always turns to the acid. No.
No, and this is kind of an abbreviated kind of look at acids and bases. Usually you have two things over here and two things over here, and one is going from an acid to a base, and one's going from a base to an acid. I guess I should say, when I said usually, that's in acid-base reactions. Sorry.
Isn't that that's like what I mean? Like, because the acid on one side, right, would lose the proton.
Right.
So then it's a conjugate base on the other side.
Right.
And then vice versa for the base. And that's always true.
Oh, yeah. Right? So did you see there are kind of two things on this side, two things on that side?
Like what I'm saying is that like the base turns to the conjugate, or the acid turns to the base on the other side. And then
But here we've got the base turning into the acid.
That's what I'm saying.
Okay, sorry. Oh
okay.
gosh. Yeah, I think you're in good shape. Okay. And because here we have acid in the base, and the base turning into acid.
It's always an acid turning into a base, always.
Is that what you asked?
Yeah, because it's losing the protons on the other side of the
Yes.
And it's always true.
But sometimes it's the base turning into acid.
Okay, yeah.
That's what I mean by vice versa.
Who's on first? Who's on second? Yeah,
We all understand.
Okay.
I think you're in good shape. I do. So Ka is the ionization constant for a weak acid, and Kb is we'll call it the ionization constant for a weak base. And Kw is the ionization constant for water, which we know at 25 degrees Celsius is 1.0 times 10 to the minus 14. All right, so this is kind of fun. If we have, and we can pick on acetate and acetic acid, if you look up the Kb for the acetate ion, the Kb for the acetate ion, and the Ka for acetic acid, you multiply them times each other, they will equal Kw, which is 1.008 or 1.0 times 10 negative 14 to 25 degrees Celsius. So for any conjugate acid-base pair. And that, yeah. Yep. So here's a little proof to kind of show you how that would work. Okay, so Hb is your weak acid. Notice it ionizing the H plus and B minus. And the Ka expression would look like this, okay, where it's the products divided by reactants. Of course, we have the conjugate base in the numerator and the weak acid in the denominator. Now, here is actually looking at the hydrolysis of water. The B negative here, that is your weak base. It's absconding onto a proton or a hydrogen from a water molecule. On the product side, then, we have its conjugate acid, and also on the product side, we have what's left over for the water, which is the hydroxide ion. The Kb expression is this, where we have the conjugate acid times the hydroxide ion in the numerator, divided by the base, the weak base in the denominator.
We only write the key A only when we have a hydrogen proton. Like, why did we write the key A and not the key B for the first reaction?
So the first is the Ka, because we are showing and it's kind of maybe back to what you guys have been saying. We know for equilibrium constant expressions, we kind of go from left to right, even though they're going back and forth. So from left to right, we have it acting as a weak acid because it's donating a proton.
Okay.
And then down here, from left to right, we have it acting as a weak base. And one of the things that I think will be helpful in kind of finding relative pHs is you're going to see me do this. I'll put Wa for weak acid, and I'll put Wb for the weak base. And then actually over here, and I'm going to put conjugate, CONJ, conjugate of, I guess I should put conjugate base of weak acid. And this guy over here, this HB on the second one, that actually is the conjugate acid of a weak base. And that's significant. And the more problems that you guys work, the more you'll see that, is because when it comes to being, how do I say this? When it comes to being, for instance, I'll take the first one. When it comes to being an acid or a base, your weak acid is a stronger acid than your conjugate base, but a weak acid is a base. So it's like strength-wise. So it's a base, but it's not as strong as this would be an acid. Similarly, this is an acid, but it's not as strong as this is a base. And actually, that comes into play because if we multiply the Ka times the Kb, it's got to be equal to Kw. And so the product is one goes up, the other goes down. One goes down, the other one goes up. Okay? But this proof is kind of try to show you how we get this Ka times Kb for conjugate acid-base pairs equal to Kw. So here's the mathematical magic. I'm going to take this quantity times this quantity and see what cancels out. So your B minuses cancel out, your HBs cancel out, and what are we left with? Just H plus and OH minus, more concentration of, which we said that is Kw. So it's just like a little proof. As long as they are related by a proton, they are a pair, conjugate acid-base pair. This is the deal. And in case I forget to tell you, which I think I probably will tell you later, sometimes you'll be working problems and you're given the Ka of something, but not the Kb of its conjugate, and you need the Kb of its conjugate. So what do? When you plug it into this, you know Kw and you know Ka, and by division problem you can get to Kb. Okay, so one goes up, the other goes down, one goes down, the other goes up. So for any given conjugate acid-base pairs, they have this relationship. Now, one thing came to mind, assuming they're at the same molarity, right? They'll have their acid or base strength will be relative. This way. All right. So this is a very busy figure, and the way this works, let's just gonna pick a couple. You go across like that. Notice that HF and F negative differ by a proton. They are a conjugate acid-base pair. We looked at this guy, conjugate acid-base pair. And it's simply saying as one gets stronger, then the other one must be weaker. So they are listed in order of most acidic in this quadrant, and most basic in this quadrant. Because if it's a strong conjugate base, then it must be a weak conjugate acid. If it is a strong conjugate acid, it must be a weak conjugate base. So when in doubt, just put the word conjugate in front of it. So, but there is a little bit to that. All right. So you might be faced with this sort of question. Remember when we did back in the beginning of Chem 2, the relative intermolecular bonds, the strength of intermolecular bonds? Yeah. Well, that's nothing to do with that. No, it is similar in that we have a whole bunch of solutions here, all 0.1 molar, and we're supposed to say what's going to be most acidic, what's going to be most basic. We're supposed to arrange them in order of increasing pH. So what's that? It's increasing basicity, basically. No pun intended. So for each one of these, what I would do is put on blinders, and you're going to see me write out in the margins what it is. So ammonia, even if you didn't know what ammonia was, the fact that they gave you a Kb value, and it's true, actually it is a weak base, and we'll put Wb there. And if you kind of go one by one, it kind of will help you identify how these are different. Okay, so here, and I think this is kind of fun. If you take a salt, ammonium nitrate salt, it should dissolve, and what's going to happen, how do I say this? You look at both of those polyatomic ions, and you're like, which one would drive my chemistry? Well, you have to think, does my NH4 plus seem like it might donate a proton? Yeah, NH4 plus will donate a proton, become NH3 and plus 1A plus. But actually then, I would call this guy, that actually is I'll go ahead and call it the weak acid. I'll do it this way, weak acid of conjugate, I know, but is that what I want to say? I guess I would say, thank you. Thanks, Benny. NH4 plus, I'm going to call it the conjugate acid. That's better, sorry. Conjugate acid of a weak base. And which weak base is it? Well, it's NH3 right above it. Now, one of the things you might say, well, NO3, nitrate, what sort of chemistry can I get going with the nitrate? Well, maybe it will accept a proton and be a base. But NO3 plus H, that gives you HNO3. And if you remember, HNO3 actually is one of your strong acids. So it's not going to do that. All right, let's see what else we got. Formic acid, it's got a Ka value. So I'm going to put weak acid there. It's going to kick off a proton. Specifically, it's going to kick on off this proton over there that's associated with the carboxyl group. Nitric acid, strong acid, SA. Now, if you put abbreviations, they don't mean anything to you, then they're no help. But hopefully strong acid, this guy's going to actually probably go at the top of that list with the lowest pH. So here we have one, sodium formate. Again, look at what sodium formate might do. Well, here's the formate ion, and I think that it's going to accept a proton. So if it does accept a proton, that would be the conjugate base of a weak acid. Sodium. Well, the only thing sodium might do would be to, it might accept a hydroxide group, but sodium hydroxide is a strong base, so it's not going to do that. It's neutral. So, Na plus is like your NO3 negative. It doesn't do anything. Okay. So here we go. Speaking of not doing anything, your sodium, there's no interesting chemistry going to go along with that. Your nitrate, no interesting chemistry. What would be the interesting chemistry? To donate or accept a proton. It's not happening. So this guy right here, actually I'm going to put neutral there. All right, do I have one more? Potassium hydroxide. Potassium, the K plus is a spectator, but of course the hydroxide. This is another example of a strong base, actually, SB. So when it comes to organizing them, I'm going to put my most acidic to most basic, and I kind of got my extremes here and the guy in the middle. Where it becomes interesting, so we're okay with this, nitric acid's the most acidic, potassium hydroxide the most basic. Where it becomes interesting are the weak acid, the outright weak acid, which is this formic acid, and then the NH4 plus was, I put the conjugate acid of the weak base. But NH4 plus is a weaker acid than the weak acid. Then we go to neutral, NaNO3. Nothing happened there, no pH chemistry. And then we go to our bases, and we're going to order them. The least basic actually is going to be the conjugate base of the weak acid. That was the formate ion, the CH3COO negative. And then we're going to have the real weak base with the KB, NH3. So as long as you can kind of, I think, categorize them, you should be fine in kind of a non-qualitative question like this. The thing about what sort of chemistry can you expect to happen, I'm going to show that to you on the next slide, next few slides. Follow up. All right. So, I guess with buffered solutions, and then more with outright acid-base reactions, we have those two parts left. You should always be able to find, I mentioned a little bit ago, not just one pair, but actually two pairs, two conjugate acid-base pairs on either side of the reaction arrow if it is an acid-base reaction. So, for instance, acid-base reaction. Notice the one-way arrow here. We could identify what's losing a proton and what's gaining a proton. And we could break up the AQs into their individual ions, like this. So the net ionic equation, the things that appear on either side of the single reaction arrow in this case actually can go away. So it looks like this. What were our spectator ions were the chloride and the sodium. So actually this would be the net ionic equation. We can identify what's losing a proton and gaining a proton. The chloride ion is losing a proton, and the hydroxide ion is picking up a proton. So kind of from left, do you guys have all these? Yeah. Okay, cool, very good. So HCl strong acid, NaOH strong base, and we have our weak base over here, proton acceptor, and kind of going from the right back to the left again. And then we have our weak acid over here, water, which would be the proton donor, going from the left to the right. Acetic acid and sodium hydroxide. And we're going to see where we do have some different sorts of chemistries going on with this sort of acid-base reaction. What gets removed from the net ionic equation are the sodium cations, or the sodium cation, that's it. So we can look at what's accepting a proton and what's donating a proton, but there actually are two acid-base pairs. NH3, weak base, spectator ion, the chloride ion, that's it. Differ by a proton, and identify who's losing it would be the acid of sorts, who's gaining it would be the base.